In this series of lectures, I am going to discuss some common mistakes that students make in the graphical sensitivity analysis. And if you have watched my previous videos on the basics of the graphical sensitivity analysis, then you must be aware that the purpose of the sensitivity analysis to look for the answers of the following two questions. The first question is that how will a change in the objective function coefficient affect the optimal solution? And second is that how a change in the right hand side of the constraint it affects the optimal solution. So the mistake number one that we are going to discuss in this video is that while making the changes in the objective function coefficients, students they do not identify the constraint lines that are not passing through the current optimal point. So to illustrate this thing, let's see an example. This example is about a manufacturing company, and this manufacturing company it is trying to evaluate a bid for producing two agri robot part. Each component must go some manufacturing processes, turning, drilling, and laser cutting. Company has limited resources in the form of the hours. Company wants to know the optimum number of these parts to maximize the profit. So in the table you can see that part A requires 4 hours of turning, 6.2 hours of drilling, and 9.1 hours of laser cutting, and the total turning hours available to them is 126. The total drilling hours are 108, and for the laser cutting they have 132 hours. So let's start the problem, and in this series of videos I will not focus too much on the graphical solution because I think it's a trivial task. The main task is to understand the graph and to see how the sensitivity analysis is done. So for graphical sensitivity analysis you have to draw a graph. So this is a must because it gives you the it helps you visualize how the changes in the constraints and how the changes in the slopes is going to affect the optimal solution. So let's start. The first thing is the decision variables. The first decision variable is, let's say, x1. This is number of part A, and x2 is the number of part B. Then we define the objective function in terms of the decision variables, and because we have the objective of maximizing the profit, so we'll write it as maximize z equal to 790 x1 plus 1080 x2, and this is subject to the constraints. The first constraint is the turning, and turning can be written as 4x1 plus 7.5 x2, and this is less than equal to 126. The drilling constraint is 6.2 x1 plus 4.9 x2. It is less than equal to 108. And for laser we have 9.1 x1 plus 4.1 x2, and this is less than equal to 132. Finally we have non-negativity constraint that tells us x1 and x2 should be greater than or equal to 0. So once we have formulated this linear program, now the next step in the graphical method is to plot these constraints. So I will just briefly show you how it's done, and so the idea is basically for plotting the constraints, we just first put x1 is equal to 0 and find the value of x2, and similarly we first then put x2 equal to 0 and find the value of x1. And in this case I have already done this. I have already found those points. So when x1 is equal to 0, x2 is equal to 16.8, and when x2 is equal to 0, x1 is equal to 31.5. For the drilling constraint we have when x1 is equal to 0, x2 is equal to 22, and when x2 is equal to 0, x1 is equal to 17.4. And for the laser, when x1 is equal to 0, x2 is equal to 32.2, and when x2 is equal to 0, x1 is equal to 14.5. Now I have already drawn this graph because, as I mentioned earlier, I will not spend too much time on this. As you can see that this is the graph, and this is how using the points of these points for turning, I have plotted the turning constraint. This is for turning, and then using the points of this drilling 0 and 22, 17.4 into 0, I have uh, I have I have plotted the drilling constraint. This is the drilling, and finally using these points I have plotted the laser cutting constraint, as you can see here. Now once we have plotted these constraints, we look for the feasible region, and the feasible region is basically the region which is shared by all the constraints. And as we can see, this is the basically this is the region which is shared by all the constraints. So once we have identified the constraints, to find the optimal solution, there are two ways to go. The first one is to draw an isoprofit line. And I have already drawn here an isoprofit line, and I have drawn it by using the some arbitrary value of by of just let me I have drawn the value of the I have drawn this isoprofit line by putting 790 x1 plus 1080 x2 equal to 10,800. It's just an arbitrary value, and when I use that number and then I put x1 equal to 0, I got x2 is equal to 10. Then x2 is equal, when x2 is equal to 0, x1 was 13.6. So using these 2 points I have plotted my objective function, or line or isoprofit line. So the idea is to push this isoprofit line, and since it's a maximization problem, push it and find the last point on the feasible region where this line intersects the boundary. Another way is to find all the values of profit at the points uh, on the boundary, and we know there is a important characteristic of linear programming that tells us that the optimum points lie on the boundary and they are on the intersection of two constraints. So two or more constraints. So here I have already identified the points, and as you can see I have labeled them as A, which is formed by the intersection of the drilling turning and turning point and the x2 axis, and its coordinates are 0, 16.8. And then there is a B point which is formed by the which point B which is formed by the intersection of the drilling and the turning, and the point C which is formed by the laser cutting and the drilling, and the point D which is formed by intersection of the laser cut on the x1 axis. So one thing I would suggest, that while drawing a graph, make sure you always write all the points on the graph, these points where these constraints are intersecting on the x1 and x2 axis, because these points will come handy when you are doing the sensitivity analysis for the constraints. So to find point B, for finding point B, which is found by the turning and the drilling, we need to find the point B by simultaneous solving of these two equations. And I have not done this maths here, and I think that you can do it by yourself. And by when I solved these 2 points, I got the coordinates for B as 7.16 and 12.98. For point C, which is found by the green and the blue line, you have to solve these two equations simultaneously to find C, and this is for finding B. And the coordinates of C that I found, you should try it yourself, is 10.6 and 8.57. So once you have found these coordinates, then you can find the values of the profits at these points. So for finding the value of z at a, what we do is simply put the coordinates of a, which is 0 comma 16.8, into the objective function, that is 790 into 0 plus 1080 into 16.8. Now I have done this before this video, so I'll just show you the final values that can be that I have calculated. So z at a, it is equal to 18,144. Z at b is equal to uh, it is equal to 19674, and z at c is equal to 1769.6, something like this. And at d I have the value of z equal to 11,455. Now based on these values, as we want to maximize the profit, so we can see that the point b gives us the maximum point, so we will say that point b is the optimal solution. So this is the graphical method of finding the optimal solution. So point b is the optimal solution. So once we are done with this, we now move to the most important thing of this video is to see is and that is to look for the mistake that people make when they are trying to find the sensitivity ranges of the coefficient. So let's see what happens for the part a. Part A, it is represented on the x1 axis, and just let me write the values of the coordinates here once again, and these values are 7.16 and 12.98, and this C is 10.6 in and 8.75. Now uh, when doing the sensitivity ranges, we need to find first the slope, and we can see that the slope of the objective function is minus c1 by c2. It is equal to the coefficient of x1, that is minus 790 by 1080. The slope of the turning is minus 4 by 7.5, and for this one it is for drilling it is minus 6.2 divided by 4.9, and for the laser it is minus 9.1 into 9.1 divided by 4.1. Now when we are trying to find the sensitivity range of part A or the x1, we know, and we discussed in our previous videos as well, that when we increase x1, when we increase this value x1, then the objective function line, that is, I have plotted here in the orange color, this slope, its slope becomes steeper, and the maximum steepness that we can achieve is equal to the slope of the steepest constraint. Now here we have these three constraints, and the laser is minus 9.1 by 4.1, and then this is drilling minus 6.2 by 4.9, and then for the turning it is minus 4 by 7.5. Now, while looking for the steepest constraint, the mistake students generally make is that they see of all these three constraints, they see that they see that this constraint, laser cutting, it is the steepest of all the three. So the mistake they do it is they simply they put the slope of this objective function equal to the slope of the laser laser constraint. So let's say for finding the value of the sensitivity range of the coefficient of x1, they will write minus c1 by 1080 equal to the slope of the steepest constraint, that is minus 9.1 by 4.1. Now, this is a mistake. Why? Because though this constraint, this laser constraint, it is the steepest among the three constraints, but see that this constraint line is not passing through point B. And as an this is one of the objective of the sensitivity analysis, that we have to keep our optimal original optimal solution as one of the solution. And so this is wrong. This is wrong. So where you have to choose only those constraints that are passing through your current optimal point. And in this case, the drilling and turning constraints, they are passing through the optimal point B. So the right way to do it is minus C1 by 1080, and this is equal to the slope of the steepest constraint, and in this case it is drilling, not laser cutting. This is not laser cutting, rather drilling, and this is equal to minus 6.2 over 4.9. So we can solve the C1, and C1 will be somewhere around 1366.5. So this is the maximum value of C1. So just from the Excel point of view, you know that the original value is 790 of for the coefficient of x1. So, and you can increase it to the 1366, so you can calculate the allowable increase by subtracting these two values, and this will come out as I think it will come out as 576.5, something 576 allowable increase. And while calculating the minimum value of C1, what we will do, we will put the slope, we will keep the C1 at its value, and then 10 divided by 1080, this is equal to the slope of the flatter constraint, because we know when the value of the coefficient of x1 decreases, the line objective function line, it becomes flatter. And how much flatter it can become, it can achieve, it can become equal to the slope of the flatter constraint, and in this case the flatter constraint is the turning constraint. So we'll write it minus 4 by 7.1 7.5, and C1 will be equal to C1 will be equal to uh, I think C1 is will be equal to 576. And similarly, you can also calculate the allowable decrease here, and that will be, the decrease is basically the original value, that was 790 minus 576, and this will be equal to somewhere around 214. So this means that if I just sum up this discussion, so the C1, the value of C1 can be varied from 576 to 1366, these two values 1366 and 576, and you will still have point B as one of the optimal solution. So basically this is the sensitivity range of x1. Now let's just see what happens when we are trying to find the sensitivity range of x2, or and in this here we are finding the sensitivity range for part B, and part B is on the x2. We know when the coefficient of x2 increases, the line becomes flatter when it x2 increase, and when x2 decrease, it becomes steeper. Now these concepts have been discussed in detail in my previous videos, so you can always go back and watch them. So for doing the sensitivity analysis of the part 2, what we are going to do here is uh, we are going to uh, we are going to keep the 790 at its original value, that is 790, and instead of 1080 we will write C2 now, and we will have to put it equal to the flatter constraint. So again, we know this is our point B, and this point B, we have to look for the flatter constraint from viewpoint of this point B. So and we can see that the turning is flatter, and the turning has a slope of -4 by 7.5, and the drilling has a slope of -6.2 by 4.9. So we will put it equal to -4 by 7.5, and we will find C2 is equal to 1481. Now the original value was for the problem was 1080. That means the allowable increase is 1481 minus 1080, and this allowable increase it's 401. This is allowable increase. And then we'll find the minimum value of the coefficient of x2, or the minimum profit for the part B, and that would be again -790 divided by C2 equal to now the slope of the steeper constraint, because it is vice versa as compared to the x1. So the steeper constraint here is the drilling, and its slope is -6.2 divided by 4.9. We will find C2 as equal to 624, and the original value was 1080. So allowable decrease will be 1080 minus 624. It will be something 624 point something, so it's somewhere around 455 or 456 something, because the original value is I have just rounded off some numbers here, so it will be somewhere around 450 456. So summing up this discussion, so the range of C2 is basically it is basically from the minimum value, that is the 624, to the maximum value, that is 1481. And if the profit of the part B is varied between these two extremes, point B will always be one of the optimal solution. So to sum up this whole discussion in this video, you have to always look at the constraint lines that are passing through the optimal solution. Don't go for the constraints that are not passing through the optimal solution. So that's it for this video. Stay tuned for the next video, and we will discuss the common mistakes the students make while doing the sensitivity analysis of the right hand side of the constraints. Thank you.